as well. I see Barry, right?
Yeah, it's a pretty empty room so far. But,
Yeah, we're only on the hour. Yeah. It's always a little awkward doing the chairing when the chair is remote, but the speakers are local. So, I don't know. I hope the speakers are local. Okay, it looks like people are still coming in. I see Sam Kumar, Tosha Swami, the other presenter in the room. Okay, I get a few minutes now, so we should get started. I don't know if Joe is there. If so, do you want to come up and get ready for the microphone while I do the introductory slides? Okay, Tasha, can you do an audio check? I see you're there now. It's taking a little while for the camera to work. Okay, I will assume that you can hear me in the room. If that's not true, please put into the chat. Welcome everybody. This is the IETF open meeting at IETF114. I'm Colin Perkins. I'm the IETF chair. Hopefully you can all see and hear me in the room and on remote. So I would like to begin with the usual note well slides. Okay, there's some echo, but hopefully it's not too bad. This is the IETF open meeting. The IETF follows the IETF's intellectual property rights disclosure rules, and a reminder that by participating in this meeting and by commenting on the presentations, that you agree to follow the IETF processes and procedures, including disclosing any intellectual property relating to the contributions that you make. I'm sure most of you have seen these slides before. The details are in the documents linked, but essentially, if you have IPR on the documents you're talking about, you need to disclose that if you're commenting on the microphone. In addition, a reminder that the IETF routinely makes recordings of these meetings available, both the online and the in-person meetings, including this one. And this meeting is being streamed live on YouTube as well as via the usual Meet ecosystem. If you're participating in person and you are not wearing one of the red do not photograph lanyards, then you consent to appear in these recordings. And if you speak at the microphones, then again, you're consenting to being recorded. And as I say, the recording is being made available on YouTube. Equally, if you're participating online and you turn on your camera or your microphone and make a contribution, then that is being recorded and you can consent to being recorded. And also the chat is also being recorded and will be made available in the usual Jabber archives. As a participant in the IETF, as I say, you acknowledge that recordings of the meeting may be made available, and that that any personal information you provide will be handled in accordance with the privacy policy. And you also agree to work respectfully with the other participants in the IETF and the IRTF. And if you have any issues or concerns about that, speak to me or speak with the Ombuds team. And the IETF's Code of Conduct and Anti-Harassment Procedures linked on the slide also apply to the IRTF. For those of you participating in person, please sign in using the mobile Meet Echo, the Meet Echo Lite tool. We're running the queue electronically, so if you have questions, then we're using the electronic queue that's accessed via the Meet Echo tool. And keep the audio and video off if you're using the on-site version, the Meet Echo Lite tool. Remote participants, please leave your audio and video off unless you're presenting or asking a question, just to avoid feedback in the session. Also, a reminder for those of you who are attending the meeting in person, as a COVID safety measure, the IETF is requiring those of you attending the meeting in person to wear an FFP2 N95 mask or its equivalent, and the only exception for that is the chairs and the presenters who are actively speaking. In particular, participants who are making comments or asking questions from the floor microphones are expected to wear a mask at all times, including while they're asking those questions. As I say, the only exception for that is the active presenter at the front of the room. Okay, so as I say, this is the IRTF open meeting. The goals of the IRTF are to complement the standards work being done in the IETF by focusing on some of the longer-term research issues. The IRTF is very much a research organization. It's not a standards development organization. And while it can publish RFCs, and we do publish both experimental and informational documents on the RFC series, the primary output of the IRTF is research, is understanding, and is research papers. The IRTF is organized as a series of research groups. Hopefully you can see them on the slide here. The Crypto Forum group and the Privacy Enhancements and Assessments groups met earlier today. The other groups sort of highlighted in dark blue on the slide are meeting later in this week. So please do look out for those groups this week and try and attend the sessions if you're interested in those topics. A little bit of research group news. I'd like to welcome Curtis Heimerl, who's recently joined as co-chair of the Gaia group, the Global Access to the Internet for All research group. Curtis will be joining Leandro Navarro, who is planning on stepping down from chairing that group after this meeting, and Jane Coffin, who is continuing. So I'd like to welcome Curtis and thank him for his service, and thank Leandro for his many years of service to the group. And I very much appreciate the effort Leandro has put into chairing the group, and I look forward to working with Curtis going forward. So thank you both. Thank you both. As I say, the IETF is primarily a research organization. We tend not to publish many RFCs. We've had one RFC published since the last meeting from the Information-Centric Networking Group, looking at architectural considerations for using an ICN name resolution service. But primarily, the IETF tends not to publish much in the RFC series, and the output is more in the form of interesting presentations and understanding and research papers. To support that, we run the Applied Networking Research Prize, and the goal of this prize is to recognize that some of the best recent results in applied networking research, is to recognize some interesting new ideas which are potentially relevant to the internet standards community going forward, is to recognize up-and-coming people who are likely to have an impact on the internet standards process and internet technologies. We're very grateful to the Internet Society, to Comcast, and to NBC Universal for their sponsorship of the ANRP that allows us to make these awards and bring people to give these talks. And what we're doing today is the goal of this session is to make some of these awards. So I'd like to congratulate Tasha Swami and Sam Kumar, who will be giving their award talks, being awarded the ANRP in this session today. Tasha will be talking first in a couple of minutes, talking about his work on data plane architectures for line rate inference, and Sam will be following later in the session, talking about TCP for low power wireless networks. We've got two really good talks coming, so please do stick around, pay attention to those, and again, congratulations to Tasha and to Sam. Going forward, look out for, there'll be more award talks. Gautam Akiwate, Corinne Kaff, and Daniel Wagner will be giving the talks at IETF114. And the nominations for the 2023 awards will be opening in September 2022. So look out for those. Look out for the nominations opening in a month or two. Okay, did the audio improve? Tried muting and restarting. Hopefully you can hear me. Okay. Okay, hopefully that's better. As I was saying, look out for the nominations for the 2023 ANRP in September this year. And congratulations to Tasha and to Sam, who will be giving their ANRP talks today. In addition to the Applied Networking Research Prize, we also host the Applied Networking Research Workshop, which we organize in conjunction with ACM SIGCOMM. This workshop is taking place tomorrow. It's co-locating with the IETF in Philadelphia. So thank you to TJ Chung and Marwan Fayed, who are the chairs this year and who've been organizing that workshop. We've got a program of, I think there are four really nice research papers, a keynote, and some invited talks on novel approaches to protocol specification. As I say, the workshop's happening tomorrow. If you're there in person, then please do consider attending. If you're attending remotely, then you can register and attend. registration is free for anyone who's also registered for the IETF, although we do ask you to register separately so we know who's attending the workshop. And the ANRW next year will be again co-locating with the IETF in July 2023, which is planned to be in San Francisco. And to finish up, before we get to the talks, I'd just like to note that we are very pleased to offer a number of travel grants for these meetings, both to support early career academics and PhD students from underrepresented groups to attend the IETF research groups, and a number of travel grants for the Applied Networking Research Workshop. Thank you very much to the travel grant sponsors, to Akamai, Comcast, Cloudflare, and Netflix for supporting that. If you'll please see the travel grants page linked from the website for details of that. And if you're interested in sponsoring the travel grants in future, or if you're interested in applying for a travel grant, see that webpage or contact me for details of the sponsorship opportunities. And again, thank you very much for the sponsors. So that's essentially all I have to say today. The agenda for the remainder of the day, we have the two ANRP award talks. Tasha Swami will be first, talking about Taurus, a data plane architecture for per packet machine learning, and that will be followed by Sam Kumar's talk on performant TCP for low power wireless networks. Okay, I will at this point switch over to Tasha. Can you check the microphone while I get the slides up?
Yes, is this okay?
Yep, I can hear you remotely. Is it working in the room?
Awesome. Should I get started?
Yes, just one second. If you have a phone, I can pass you control so you can control the slides yourself if you have the Meet Echo Lite. If not, then shout when you want to go to the next slide. Okay, so I should have control over that. While Tasha is checking to see if that works, I'd just like to say that as I say, the first talk today is Tasha Swami, who'll be talking about Taurus, a data plane architecture for per packet ML. Tasha is a PhD candidate in the electrical engineering department at Stanford. His research is focusing on the intersection of machine learning, networking, and architecture. And he works on the hardware-software stack for data plane-based machine learning infrastructure and applications. Tasha is due to graduate this year. I understand he's on the job market. So if you like this work, then please do talk to him. He'll be around at the IETF all week. And if you find this talk interesting, I believe he's also going to be presenting in the CoinRG session later this week. Tasha, over to you.
Awesome. Thanks, Colin. Cool. So I'm going to be talking about Taurus, which is a project that me and my colleagues have been working on. And so Taurus is essentially a data plane architecture for per packet machine learning. And go into a little bit of what that means. All right. So this here is a quote from a 2015 Google blog. And at that time, Google was already dealing with over 1 petabit per second of total bisection bandwidth. And it's only grown larger and harder to scale since. So what we're essentially dealing with here is a situation where networks require more and more complex management with higher and higher performance. And so it's the time is ripe for finding new solutions here. And one of the promising solutions in this area is machine learning. So machine learning can allow us to essentially take in data from the network and make progressively better and better decisions as we train our models. And these machine learning algorithms can approximate network functions based on the data they see, and they're also going to customize their operation to the data that they're training on, which in turn means that these machine learning algorithms are actually customizing their models to the network itself. And so we're sort of doing elements of this already with handwritten heuristics in the network. So something like an active queue management algorithm, or hashing and load balancing, and playing with operator tuned parameters. So all machine learning is doing here is taking the next step by automating the search for these kind of parameters that allow it to work well within your network. So if we're okay with using machine learning, we now need to examine where exactly in the network it has to happen. So I'm sure many of you are already familiar with software-defined networks. Essentially, the control plane and the data plane are split, and the control plane is responsible for policy creation, essentially in the form of flow rules, which are installed into a data plane, that's where you're going to find your switches, and they're doing packet forwarding via match action. So right off the bat, there are two good candidates for where we should operate with machine learning. And on the left here, I have a diagram of the same typical software-defined network. But on the right, I have a software-defined network with the torus worldview. And so what we've actually done here is we've split the machine learning operation into training, which is going to happen in the control plane, and then inference, which is going to happen in the data plane. So in the control plane, policy creation is going to take the form of flow rules plus ML training. And when installing this information into the data plane, it's going to be sending flow rules as usual, but also the ML model weights. And in the data plane, we're going to be doing our typical match action packet forwarding, but we're also going to be doing decision making with ML inference. And so that brings me to one of the core tenets of Torus, and that's essentially that ML inference should happen per packet in the data plane. And so the intuition here is relatively straightforward. You want to be able to do per packet operation because that is the finest granularity of traffic, essentially operating on a packet scale. Now, not every application may need per packet level operation, but there are applications that need it, and so the platform should be able to support per packet operation. And then the data plane, that's where the packets are. So if we're going to be doing decisions on packets, it should happen in the data plane. Oh, I think PowerPoint animations don't play well with the PDF. So that's okay. What's basically happening in here is that if we were to do just a rough off the cuff math here, so you have traffic at 1 gigapacket per second moving through your data plane. Now, in the time it takes you to send a packet digest from the data plane up to the control plane, calculate flow rules, and then install it back into the data plane. In this case, we've assumed half a millisecond for each step. So we've now missed 1.5 million packets in our traffic stream by the time we had flow rules installed into the data plane. So in the example here, we're doing anomaly detection. So we're trying to find out if incoming packets are malicious or benign. And maybe if we find that it's malicious, we're going to install some rule to say, block that IP. And so if we've missed 1.5 million packets during this flow rule installation time, by the time we block that IP, we've already let a ton of potentially malicious traffic into the network. So the whole takeaway here is really just to show you why we can't let our operation for this level of application happen in the control plane. And if we're committing to using machine learning, we can't have inference happen in the control plane. So fundamentally, the conclusion here is that the robustness and performance of your network are going to be determined by the quality of your reaction and the speed of your reaction. So in the machine learning worldview, the quality of the reaction is going to be determined by your training data. So how much do you have? What kind of cases does it cover? How well is it cleaned? But also your speed of reaction. So in the case of the anomaly detection, you want to act on a malicious packet the moment you see it. You don't want to have to go to the control plane and come back and install any sort of flow rules. And this is essentially the per packet operation in the data plane. So zooming in on the control plane, let's talk a little bit about the actual implementation of how you do this. So I mentioned before that we're going to split our machine learning into training in the control plane and inference in the data plane. And so the key here is that training is off the critical path. If packet forwarding is happening in the data plane, then the control plane is not responsible for making per packet level decisions, which means that we can do our machine learning training there at leisure. And essentially we can put in whatever the latest and greatest ML accelerators are, whatever your favorite ML framework is, install it in a control plane server and have it training models offline. The trickier part comes in the next step, where now we need to deal with the actual critical path, basically tackling packets as they come. So machine learning inference here is going to happen in the data plane, like I mentioned. And the final outstanding question here then is, if we're okay with doing training in the control plane, we can use whatever existing hardware we want. And then what do we do about the data plane? Do we have, say, a switch that can do inference at line rate per packet operation? And so this is really the crux of Taurus, and that's what it aims to do. So Taurus is an architecture for per packet machine learning inference in the data plane. So let's jump into the actual hardware and how we enable this kind of machine learning inference at line rate. So I have a picture here of a piece of pipeline, a protocol independent switch architecture. So this is the typical programmable structures you'll find in these kind of switches. So some sort of programmable packet parser, match action tables that allow you to encode your network functions, and then maybe a programmable traffic manager. So we're going to actually keep most of these elements and just make a modification of additional hardware that'll allow us to do our machine learning inference. But the natural question is, if we're committing to adding hardware into the switch pipeline, what does that look like? And more specifically, what is the abstraction here with which we're going to create our programmable machine learning fabric? And so in Taurus, we use the MapReduce abstraction. So MapReduce is really useful for machine learning because it supports a lot of the common linear algebra operations that you need for your ML algorithm. So this covers everything from neural networks, support vector machines, k-means, all these different kind of applications. And just as an example, I have here in the picture an example of a single neuron from a deep neural network. So you can see exactly how map and reduce are applied here in this case. In the blue box, we are doing an element-wise multiplication. That's our map with multiplication with inputs and weights, and then we're applying a reduction. And so this is going to essentially add all the values together, and you're going to produce a scalar value from your vector of inputs. And then finally, we're going to apply an activation function. And so that suffices for a single neuron, but you can mix and match this pattern ad nauseum to create a full neural network. So by stacking extra of these blocks in parallel, you'll be creating a layer of neurons, and then stacking them sequentially, you'll be creating multiple layers. And so that's how you can create, say, a deep neural network. So the other advantage of the MapReduce pattern is comes from the kind of performance that it enables. Primarily, it's from the SIMD parallelism. So it's same instruction, multiple data. So we can get a lot of performance out of the parallelism with minimal logic. And this is as opposed to what you might find in say like a typical like Tofino pipeline where they have VLIW pipelines, which give you much more flexibility. But the cost here is that there's a lot of logic that's needed for the communication hardware. And that ends up taking up a lot of the overall on-chip area. And in addition, SIMD parallelism gives us the ability to unroll the loops in our algorithms. So the idea of unrolling here, if we take the example of say a single layer of a neural network, and say you have 4 neurons in your network, you can either execute them sequentially, you're doing one neuron after the other, or if you have the resources, you can instantiate all 4 of them in parallel. And so the trade-off here is that more unrolling is going to give you better performance, essentially doing all 4 of those neurons at once, while less unrolling means you only need the hardware for one single neuron's worth of operations, but it's going to take you 4 times as long. So it's less resource intensive, but it's also much less, a much higher latency. And but we get this kind of control with the SIMD pattern by essentially adjusting unrolling factors. So we went ahead and we essentially adjusted the switch pipeline with a MapReduce unit that implements the patterns that I just described. So we still have our typical programmable elements. So we have a programmable packet parser, match action tables, and traffic manager. But you can see in the center, we have this MapReduce unit. And that's essentially what's going to do our machine learning inference. And so there are a couple little idiosyncrasies about the arrangement of the pipeline that I want to point out. And that's how we use these different elements for machine learning context, even if they're typically network elements. So a packet parser is normally for pulling out your headers from your packets and doing whatever you want with your match action rules. In this case, packet parsing is also pulling out the features for our machine learning inference. And then we have match action tables before and after the MapReduce unit. And so these are doing different types of rule-based pre and post-processing on our machine learning inputs and outputs. So the match action tables before MapReduce can be doing some sort of cleaning on the features, and then the match action tables on the output on the right side of the MapReduce unit can be doing some sort of interpretation of the results. And so when we actually went to design this MapReduce unit, there's a couple of things that came up. It turns out you can't really just stick an accelerator into the switch pipeline. So what we did was we kind of established what were the points that we wanted our MapReduce block to fit. And so most of all, we wanted it to be reconfigurable. So essentially, you should be able to program it. It can't be an ASIC for a single type of machine learning application. You should be able to put in whatever or program whatever application you want. Oops. And it has to meet line rate with the fixed clock. So this essentially rules out an FPGA because an FPGA will give you a variable clock. We want it to be deterministic. And of course, line rate is our performance requirement. And then minimal area and power overhead. We don't want to blow up the entire chip area, adding in like a MapReduce block. It should be something that is small, but gives you access to a whole class of applications. And so finally, the one little thing to note here that's kind of interesting is that most of these ML accelerators are built to do batch processing in an effort to get high throughput. But in the network pipeline, you're actually processing packets as they're coming, which means that you're operating on a batch size of 1, which is, turns out, puts a lot of different performance demands on the hardware than a typical accelerator would see. Yeah, so I have a quick example here just to make this a little more concrete. Going back to anomaly detection, so you can imagine, say, a packet coming into the switch pipeline, and we want to see essentially whether it's malicious or benign. So the packet hits the first stage, and that's where we're going to do our packet parsing. So we're going to read local features, say our IP, whatever information we can extract from the packet itself. The packet is going to move to the second stage, which are the match action tables. And from there, maybe we're going to do some sort of retrieval of out-of-network events. So these would be different kinds of elements of metadata that the control plane may have installed into the match action tables. So something like the failed logins per IP. The packet then moves to the center block, the MapReduce unit. That's where we're going to apply our learned anomaly detection. So you can imagine this is maybe a binary neural network, and it gives it a score from 0 to 1 on how anomalous it is. So 1 is definitely anomalous, 0 is benign. And finally, the match action, or the packet will move to the post-processing match action tables, and that's where we do our interpretation. So say we got a score of 0.8, so it's pretty anomalous, and now we want to drop it or quarantine it. This is where the match action table will set a rule for that, such that when the packet now moves to the traffic manager, it's going to go to the appropriate destination. So in the paper, we actually did a full ASIC analysis of this Taurus hardware and how we can, we wanted to show essentially that it has minimal overhead and it's feasible to build something like this. And so we based our evaluation platform on a coarse-grained reconfigurable architecture called plasticine, and we programmed our applications in the spatial hardware description language. And so spatial is just an HDL that lets you use these kind of parallel patterns like map and reduce to program your reconfigurable architectures at the loop level. And so the basic architecture of the MapReduce unit here is really just a grid of compute and memory tiles. So easily scalable and very, very straightforward. In the compute units, we have SIMD lanes that are operating in parallel and a reduction network that allows us to implement the reduce operation. And the memory units are just blocks of banked SRAM. So we're doing severe pipelining within the compute unit, but then we're also doing pipelining one level higher between the compute and memory units. So the idea here is SIMD parallelism everywhere, and then pipeline parallelism everywhere. And that's how you get your performance, really. So we went through a set of real-world applications and programmed them onto our ASIC. And we ended up using a 12 by 10 grid to support all of them. And we compared it to state-of-the-art switches with 4 pipelines. And our reference switch was 500 square millimeters. And we found that our grid, which could support these different applications, was only adding a 3.8% overhead, or 4.8 millimeters per pipeline. So again, before earlier I said we want minimal area overhead. So 3.8 is pretty low, given that you're now getting an entire class of machine learning applications. And jumping into one of these applications, I've been using anomaly detection as a recurring example here. We tried out 2 different types of anomaly detection with support vector machines and a deep neural network. And so for both models, you can see in the throughput, it's 1 gigapacket per second, which is the line rate for high-end switch pipelines like your Tofinos and Broadcoms. The latency that we added was in the hundreds of nanoseconds or less. So in this case, you would choose your application. You can see here that the BSVM requires 83 nanoseconds, while the DNN requires 221 nanoseconds. So depending on your SLOs and what kind of requirements you have to meet, you can choose your algorithm to reduce latency. And then in both cases, the area and power overhead required for the hardware to implement just these applications is single digits or less. So 0.6% power overhead, 0.5% area overhead, or 0.8 and 1.0 respectively. Again, if you don't need, say, the full suite of benchmarks, you only want a reconfigurable fabric that will let you do anomaly detection, you can do it with minimal overhead here. And so in the paper, there's several more applications if people are interested, such as a congestion control network and a traffic classification network. So we went through this whole process of doing an ASIC analysis to prove that it could be done. But as far as research goes, we don't really want anyone waiting for some sort of mass-produced Taurus ASIC. So we've put out an open source FPGA-based testbed. And so this is just a rough diagram of what it looks like. At the control plane, we're using your typical network OS like ONOS. We're using a Tofino switch to mimic the PISA pipeline elements like your programmable packet parsers, match action tables, and traffic managers. And then we're using an FPGA to mimic the MapReduce unit. So we set it up in this bump in the wire configuration. And so because of the limits of an FPGA, you're not going to be able to hit the same performance as you're going to get with the ASIC coarse grain reconfigurable architecture, but it's there to serve as a proof of concept for the functionality. So just a quick demonstration of this test bed. We did an example, essentially the example I mentioned earlier about anomaly detection, where we're trying to do detection of anomalous packets in the control plane, or we're trying to use Taurus and do anomaly detection in the data plane. And so with the testbed that I just showed you, you can do either. So in the case of Taurus, we'd be placing our anomaly detection application on the FPGA, while if we're trying to do control plane based anomaly detection, we would run it at the controller on the CPU. So the takeaway here is the same sort of message on why you really can't use the control plane for efficient machine learning based decision making. And if you take a look at the very last two columns, the F1 score, now this is the F1 score for the model when it was implemented on the baseline, which is control plane, or Taurus, which was in the data plane. And in software, in TensorFlow, the F1 score is 71.1. So you can see that Taurus on the far right side of the table is achieving an F1 score of 71.1. So it's faithfully recreating the model as it was in software. And we're processing packets as they're coming in. Whereas in the control plane, we actually had to sample packets from the network and run it through the control plane and run it through an ML framework and try to install flow rules. And what ends up happening is that you miss so many packets while doing this operation that your effective F1 score drops pretty heavily. So you can see on the far right column, the F1 score for the baseline ranges from 1.5 to almost 0. So you're effectively throwing away your model because of the added latency. So that's just one example of what we did with our FPGA testbed. There's of course lots of other things you can do, but just to reinforce the point why you have to operate in the data plane. Cool. So yeah, so that's mostly it for me. I have my contact information here, and I have at the bottom a GitLab link for the FPGA testbed. We hope people can try it out. And there's the link to the full paper in this easy to memorize URL. So, yeah, I'm happy to take any questions.
Okay, thank you very much for the excellent talk. Since we have some people remote and some in the room, I think if we can manage the queue using MeetEcho, the MeetEcho queuing tool, I think that would be helpful. I do see, I guess it's Barry at the microphone there.
Okay, actually, I'm being Dave Oran right now. Dave Oran asks, I assume the class of anomalies you can detect are those that can be detected by header fields within the width of the ALU of the switch. Things in the packet data beyond the headers won't be seen. Is that correct?
So in the case of anomaly detection, we used the KDD NSL dataset, which had a record of different attacks that were calculated from, like you said, either header fields or you can also actually calculate aggregate fields from across headers. So you can say create like a histogram using the match action tables across different packets. And the packets, the packet headers are going to be limited by the packet header vector size that's moving between stages in the switch pipeline. But you don't necessarily need to be limited to features in the header because the control plane can install different types of metadata into the match action tables, and you can do your own processing in the match action tables over time, or whatever other kind of calculations you want to do on your headers. So the headers are just the starting point for the features here.
Hi. Is this working?
Okay.
Yeah. George Michelson, can I sneak two questions in? Is that okay?
Yeah.
So the first one, and this is the naive attendee question, I suspect the paper is very important for interpreting that last table. It was really quite opaque how to understand the meaning of the columns and their impact on a comparison to the baseline. I think there's a lot of implicit knowledge in your table structure.
Sure.
I'm sure the paper explains it. The slide where it was just a bit obtuse to a naive reader. So at the start of your talk, that was the first point. You made a case to say that the delay between doing a packet sample, constructing table match rules in the controller, injecting those rules down into the functional plane and applying them, had a huge packet loss and mismatch interval. But it seems to me the delay to perform the ML operation, tune your ML, have a model that is representative of the condition you want to model, and then install that, has a similar cost. It's not to say there's no benefit of ML. I think it's huge. But the component that's about the delay cost of doing an instantiation of rules, I don't think is a basis of doing it. I think you're on stronger ground arguing it's about the ability to do complex match at line rate than the static cost of doing the rule installation.
Right. So the installation, you're right about the installing the model itself. So the idea is that you could be sampling packets from your network and be sending different kinds of metadata to the control plane and essentially be doing your training offline. And you can install model weights or replace model weights as needed. The idea is that whatever is operating in the data plane itself has nothing to do with the installation of model weights. It's completely agnostic of the control plane.
I thought that idea that you could do the model training asynchronously at a sample
Exactly,
rate is
yeah.
very beneficial. But if you consider a new class of attack, that you have to understand it and do some form of Bayesian analysis and classification, which is completely unmodeled here. Exactly how you do that training, unknown. How long that takes, it's not about the speed of the chipset, it's about your ability to do the good bad classification a priori to inform the model and then download it. That's quite a high cost in time.
Yeah, so this is always like kind of the trouble with security, right? Like if you want to do an on-the-fly analysis of a brand new attack, that's not really what we're targeting at the moment here. But
but in engineering terms, your case, this is extremely fast at line rate. Well made. I enjoyed listening to it a lot. Thank you.
Thank you.
So, excellent work, Tushar.
Mhm.
I have a question. Doing machine learning in data plane will consume more energy.
Sorry, I can't.
Using machine learning in the data plane
Mhm.
will consume more energy.
Mhm.
So, and we would like to reduce the energy consumption of
Sure.
routers and switches. So, have you looked at this issue?
Yeah, so I think the for energy consumption needs to be looked at maybe more holistically. So while you are increasing by some small percentage the energy that you'd be consuming in the switch itself, you can consider that, say, if you're doing anomaly detection, you're removing the cost of running an anomaly detection application and software on a server somewhere else. So with this like specialized hardware here, you're consuming less power in the switch than you would running it in software elsewhere. So on the whole, you're reducing power costs, but for the switch itself, yeah, you'd be increasing it minimally.
Okay. Thank you.
Okay, thank you. Anyone else have questions for Tasha? And I guess while we're waiting for that, I have a question. I mean, this is an IETF meeting, which is co-locating with the IETF. And obviously, since this co-locates with the IETF, the question is then, to what extent have you given any thought towards how this might change or affect the type of work the IETF does? Are there any implications of these types of systems for the way we design standards or the types of protocols the IETF designs? Or is this just an optimization that fits within the existing architecture?
Yeah, I think so. One of the things that actually Hashem, who asked the question earlier, brought to my attention was what kind of standardization is needed for packet headers if we're going to be using them as features or carrying model weights or basically doing kind of this like ML assist type operations. So I think there's probably something there as far as making a cleaner definition of what has to happen at the packet standardization level to support this kind of machine learning and make it easier for different types of ML systems to interoperate.
Yeah, that makes a lot of sense. Thank you. Presumably, there's also something in terms of the control plane and the standardized sort of programming model for that in order to specify the model. Is that right?
Sorry, I didn't.
I mean, I'm thinking that your traditional programmable switch uses P4 or something like that as a programming model. Do we need a similar standardized programming model for these types of ML switches?
Oh
Or
yeah,
is it
so as like kind of a complement to P4, we went with MapReduce. So we're not necessarily married to the idea of using a MapReduce block or anything. The bigger idea here is just doing inference in the data plane. But yeah, it could definitely help to have some sort of standardization in the way that P4 works, but for the MapReduce elements. So you could even consider like an extra control block in P4 as MapReduce, and we have another paper in submission on what the language level constructs here look like. So yeah, it's definitely an area for standardization as well.
all right? Great, thank you very much. Are there any final questions? Okay, I don't see anything. So thank you very much. All right, Sam, if you can come up while I try and share the slides. right, can you see the slides?
Yes, we can see the slides here.
Okay. All right, so with any luck, you should now have control over the slides. Have they gone away?
I see. So that's,
Is it working?
I can see it on my, oh yeah, I see. I had to click share.
Ah,
Okay.
here we are. Just took a little while. Yeah.
So,
Okay,
yeah.
so okay, great. All right, so the second talk today is focusing, I think, on a very different problem domain. So in this talk, Sam Kumar will talk about his paper on performant TCP for low-power wireless networks. This was originally presented at the NSDI conference in 2020, if I remember correctly. Sam is a PhD student at UC Berkeley, advised by David Culler and Rolaka Irtfopen. He's broadly interested in systems, security, and networking, and his research focuses on rethinking systems designed to manage the overhead of using cryptography, and presumably also improving the performance of TCP for low-power wireless networks. So, Sam, over to you.
Okay, thanks, Colin, for the introduction. As you said, I'm Sam, and I'm going to present my research on performant TCP for low-power wireless networks. And this is a joint work with my collaborators at UC Berkeley. And as you mentioned, it was published in 2020 at NSDI. So I'm going to begin by giving a brief overview of history of research in low-power wireless personal area networks, or LOPANs, to put our research in context. So LOPAN research began in the late 1990s, and at this point in time, researchers deliberately cast away the internet architecture based on the idea that LOPANs may have to operate in two extreme environments and two different from regular networks in order for the internet architecture to directly apply. So many of the early protocols like SMAC, BMAC, and so on, and the early systems like TinyOS and Contiki did not conform to any particular standard or architecture. And this allowed the researchers to nicely explore how to tackle the challenges of LOPANs without being hindered by having to conform to an architecture. About a decade later, in 2008, IP, the Internet Protocol, was first introduced into space, largely enabled by the 6-LOPAN adaptation layer standardized by the IETF. And what happened here is that people found ways to take the lessons that were learned in the earlier systems and apply them within an IP-based architecture. And this essentially caught on. In a few years, by about 2012, IP had essentially become the standard in the space. But surprisingly, the adoption of IP did not come with TCP. For example, OpenThread, a low-pan network stack developed by Nest and used in the smart home space, didn't even support TCP. And instead, the community has come to rely on protocols like CoAP, which are specialized low-pan protocols based on UDP. It's also worth pointing out that during this time, LOPANs have not yet achieved the same kind of pervasive adoption that we've seen in other protocols like Wi-Fi, at least in the context of granting internet access to devices. So a natural question is whether to get that kind of pervasive adoption of LOPANs, we should adopt not only IP, but also the broader set of IP-based protocols, including TCP. In this context, our work completes the transition of LOPANs to an IP-based architecture by showing how to make TCP work well in LOPANs. And our research artifact is TCP-LP, a performant TCP stack for LOPANs. So what exactly do I mean when I say performant? Well, one metric is goodput, and that's the amount of bandwidth that an application is able to get when operating over a TCP connection. Now, there have been a few prior attempts to use TCP in the space, typically based on a simplified embedded TCP stack like micro IP or blip. And what we can see in this graph is that our work, TCP-LP, achieves significantly higher goodput than prior attempts to use TCP in this space. In fact, we can calculate an upper bound on goodput, shown by these dashed lines, based on measurements of how fast the radio can send out packets and how much overhead is lost to headers and ACKs and so on. And our work comes quite close to these upper bounds. I'd also like to share an update that's happened since we published this research, which is that OpenThread, the low-power network stack that I mentioned that's used in the smart home space, We simply adopted TCP directly based on our research. It uses TCP/LP as its TCP implementation, and our research also influenced Thread, the network standard that OpenThread implements. So I'm delighted to have been invited to help spearhead this process, and I am hopeful that, that the adoption of TCP in this space will help improve the adoption of low PANs more broadly in the smart home space. So now I'm going to take a step back and provide some more context as to what exactly low PANs are and what some of the challenges are with using low PANs. And I can do that by comparing low PANs to other wireless technologies that you might be more familiar with. So on the left, Wi-Fi provides a host with internet access via an access point. In the middle, Bluetooth doesn't really provide full internet access. It's more like a cable replacement channel, a wireless USB of sorts. And then on the right, we have low PANs, which aim to provide internet connectivity at the same level as Wi-Fi would, but to embedded devices and while operating within the constraints of low power. For example, having to transmit data over multiple wireless hops to set up an embedded mesh network. So low PANs have been used in a variety of applications. For example, scientific applications like environmental monitoring, structural monitoring of a bridge, and it's also been deployed in the indoor environment in a smart grid context. And recently, there's been a push to deploy it in the smart home and IoT space, and the Thread and OpenThread efforts I mentioned earlier are one such attempt. But despite being useful for all these applications, it's difficult to use low PANs because they also come with a set of challenges. The first set of challenges come from the resource constraints, the fact that the embedded hosts have limited CPU and memory resources. The second set of constraints come from the link layer. Low PAN link layer, like for example, IEEE 802.15.4, has a small MTU of only about 100 bytes and has low wireless range, which means that in order to get connectivity over a large area, you need to transmit data over multiple wireless hops. And finally, energy constraints are also an issue. You typically don't have enough energy to keep your radio on and listening all the time, so you duty cycle your radio. What that means is that your radio is actually in a low power sleep state for say 99% of the time, and then 1% of the time you can turn on your radio to send or receive packets. And in order to provide an always-on illusion to applications, despite doing this to save power, we need some careful scheduling at the link layer in order to make sure the data is only sent to a node when its radio is on and ready to receive that data. So to make this more concrete, I'm going to tell you about the platform we used in our research. It's called Hamilton, and some of the stats of this platform are on the slide. The key point here is that this kind of device is more powerful than the devices we had when low PAN research first got started in the early 2000s, but it's still substantially less powerful than even a Raspberry Pi. You cannot run Linux on a device like this. Instead, you have to run a specialized embedded operating system. And you can understand our research as tackling the central question of how should a device like this connect to the internet? And the result of our research is that we show that TCP IP works well. Now, as I mentioned earlier, the adoption of IP in this space did not include TCP, and that was no accident. The reason is that researchers had doubts as to whether TCP would work well, and they expected it to not work well given the challenges of low PANs. So here are some quotes I've taken from some research papers to show some of the concerns that the community has had about using TCP. The first one is that TCP is not lightweight and may not be suitable for implementation in low-cost sensor nodes with limiting processing memory and energy resources. The second one is that certain features of TCP may cause harm. Like for example, that the connection-oriented protocol aspect of TCP is a poor match for wireless sensor networks, where actual data may only be in the order of a few bytes. And finally, there's the wireless TCP problem. The idea that TCP may use a single packet drop to infer that the network is congested, which can result in extremely poor performance because wireless links tend to exhibit relatively high packet loss rates. So again, to summarize more simply, there's concern that TCP is too heavy, that its features are necessary, and that it'll perform poorly in the presence of wireless loss. So central to our research was understanding TCP's performance. And what we did is we did a study where we actually ran TCP in a low PAN, measured its performance, and tried to draw conclusions about how well TCP really does or does not perform. And what we found is that out of the box, TCP indeed performs poorly, but it turns out it's not due to the expected reasons that people had. The actual reasons were somewhat different. Okay, so the actual reasons are that low PANs have a small L2 frame size, basically a small MTU, and this results in very high header overhead. The second problem is that hidden terminals are a serious issue for TCP when operating over multiple wireless hops. And finally, that the kind of scheduling at the link layer needed to support a low duty cycle and low energy consumption interact poorly with TCP. Now, there's a key difference between the issues on the left and the issues on the right. The issues on the left, if they were to exist, would be fundamental issues. There's no clear way to adapt TCP or the link layer to eliminate those issues. But the issues on the right, it turns out, are fixable within the paradigm of TCP via fairly straightforward techniques. So in our research, we show why the expected reasons don't actually apply. We demonstrate techniques to address the actual issues causing poor TCP performance. And our overall conclusion is that TCP can perform well in low bands after all. So that's an overview of what I'm going to be telling you about. And there are also, by the way, a set of techniques that we propose in order to make low bands work well, which I'll go over in the course of the talk. Okay, in the next part of the talk, I'm going to focus on the expected reasons for why the expected reasons for poor performance don't apply. And to go back here, I'll be talking about this technique in this part of the talk. And the reason is that this part of the talk is more about our experiments and our observations about the expected reasons. This technique has to do with our implementation, which is why it's included. I'll talk about the remaining techniques in the next part of the talk, where I dive into how to fix the actual reasons for poor performance. So our methodology is based on a Hamilton platform, as I mentioned earlier. You can see the picture there. This is a Hamilton platform connected to a Raspberry Pi, and the Raspberry Pi is just there as a back channel to collect logs and so on, and measurements. The TCP stack was, of course, running on the Hamilton platform directly. Our software stack is using OpenThread with Riot OS, and we used a wireless testbed to collect our data, where each of those numbers is one of our Hamilton nodes. The lines connecting them show an example of a topology. In reality, OpenThread is going to generate this dynamically. This is just a snapshot of what it might look like. And we ran TCP, where one TCP endpoint is in the wireless mesh on one of the Hamilton nodes, and the other TCP endpoint is hosted on the cloud in Amazon EC2. So one of the first things we had to do was to implement TCP. Now, as I mentioned earlier, there have been several prior attempts to use TCP in this space based on simplified embedded TCP stacks, but we wanted to use a full-scale TCP stack in our study. Now, the challenge is that implementing a full-scale TCP stack is hard, and in fact, there's an entire RFC devoted to describing all the problems that people were seeing in full-scale TCP stacks back in 1999, even though these TCP stacks had matured for at least a decade by this point. So our approach was not to implement a TCP stack from scratch, since we felt it would be too error-prone to do. Instead, we started with the mature full-scale TCP implementation in FreeBSD and re-engineered key parts of it so it would work well on an embedded platform. And we call our resulting implementation TCP LP, where the LP stands for low power. So now that we have our implementation of TCP, we can concretely answer the question of what are the resource requirements of running TCP. So what we found is that TCP LP requires 32 kilobytes of code memory and about half a kilobyte of data memory per connection to store all of the TCP connection state in a full-scale TCP implementation, while our platform has substantially more code and data memory than that. Now, as an optimization, we use separate structures for active sockets that are actually endpoints of a TCP connection and passive sockets that are just listening for new connections, which helps to save a bunch of memory as well. But the point here is that, at least in terms of connection state, we're well within the bounds of the available memory. So natural question is, what about the actual buffers used to send and receive data? So the TCP buffers need to be the bandwidth delay product in size in order to be able to send at full speed of the network. And we empirically determined the bandwidth delay product as 2 to 3 kilobytes. And we can see in the graph here how we experimentally did that. You can see 2 to 3 kilobytes of buffer size, the available output over TCP levels off. So our conclusion here is that TCP, including the size of the buffers, fits comfortably in memory. And in fact, there's another conclusion to be drawn here, which is that if you notice, the size of the buffers is actually much bigger than the connection state, which suggests that most of the overhead of TCP doesn't come from the complexity of the protocol, it's from the buffers. And any performant bulk transfer protocol would need these buffers in order to transmit at the BDP. So in some sense, the overhead really isn't bottlenecked by TCP's complexity at all. There's also we also introduced a technique here in order to reduce the memory used for the buffers. And part of this has to rely on TCP having both a receive buffer and a reassembly buffer to store in-sequence data and out-of-sequence data for reassembly. Now, full-scale TCP stacks like FreeBSD use packet queues, use a separate queue of packets for each of these. But in the embedded setting, we don't want to use dynamically allocated packets, because if we hold on to dynamically allocated packets in a memory-constrained setting, we may cause other memory allocations to fail. So instead, we want to use flat arrays. And the naive strategy would be to have a separate flat array for your receive queue and for your reassembly queue. Now, to optimize this, what we observe is that there's an interesting relationship between the advertised window size, the number of bytes we currently have, and the total size of the buffer, which is that the number of received bytes plus the advertised window size is equal to the total size of a receive buffer. Now, the observation we make on top of this is that all of the data we may possibly get for reassembly has to fit within the advertised window size. That's the contract of TCP, that if you're sending to a recipient, you should not go past their advertised window. So this allows us to actually store the receive buffer and the reassembly queue in a single flat array. Okay, so the way this works is that we have our flat array, and the yellow region with the start and end pointers is just a circular buffer to store our in-sequence data. And as we receive out-of-sequence data that needs to be reassembled, we store it in the same array past the end of the circular buffer, using a bitmap to keep track of which of these bytes are active, corresponding to received out-of-sequence data, and which of them are just empty slots on the array where new data can be stored. Okay, so in this way, we can significantly reduce the memory for buffers by, in some sense, not having to allocate a separate buffer for a reassembly queue and just sharing that with the buffer we've allocated for the receive queue. Okay, next I'm going to talk about the wireless TCP problem. And before we talk about that, I need to tell you about the number of in-flight segments, since that affects TCP's congestion control. So as I mentioned, the bandwidth delay product is 2 to 3 kilobytes. Each segment is sized to about 250 to 500 bytes. And this was chosen carefully. It's actually based on the technique I'll tell you about later on in the talk for coping with the small MTU of these networks. So I'll come back and explain this, but for now, take it as a given that our segments are 250 bytes to 500 bytes. And what this works out to is we have 4 to 12 in-flight TCP segments at any one point in time. Now, this is different from other higher bandwidth networks. You might imagine if you're transmitting over a higher bandwidth network or over a longer distance, you may have hundreds or thousands or tens of thousands of packets in flight. And in comparison, 4 to 12 is very small, and that profoundly affects how TCP's congestion control operates. So here are some examples of TCP neutrinos behavior in a low band. And for now, focus on the left graph. Here, our maximum segment size is 462 bytes. And what's going on, and when I say maximum segment size, I'm actually subtracting the space for TCP options. So this is how much data is sent in each TCP packet. And our bandwidth delay product is filled by just 4 TCP segments. So what ends up happening is that, yeah, our losses are very frequent, but because we only need a congestion window of 4 segments in order to fill up the BDP and send at line rate, TCP's congestion control is actually able to recover from losses extremely quickly, and we spend most of our time actually sending at a full window, despite the losses in the wireless medium being frequent. On the right, we have a more challenging scenario where we size our MSS to be smaller, and we use some active queue management, which induces some more loss events. But we still find that TCP is able to reach a full window and operate there most of the time, despite seeing frequent losses. So somewhat counterintuitively, we find that because our bandwidth in these networks is so small, our bandwidth delay product is small, and as a result, we can recover to a full BDP quickly after a loss. And this means that the wireless TCP problem actually does not affect TCP's performance significantly in these networks. And it's much more resilient to wireless losses in a low band than it is in a higher bandwidth wireless network. So that was a surprising result, but one that works well for us because it removes one of the obstacles we'd ordinarily would have faced in getting TCP to work. So now I've talked about why the expected reasons don't apply. In the next part of the talk, I'm going to tell you about the actual reasons for poor performance. And going back to our slide with our techniques on it, I'll be telling you about these 3 techniques. Now, there are a couple I didn't get to, the zero copy send buffer and the link layer queue management, and that's because I don't have the time in this talk to talk about it. But if you want to chat about it afterwards, I'll be around, or you can look in the paper to find some details about those. So first, dealing with the MTU problem, here's a graphic showing the size of the MTU in Ethernet, Wi-Fi, and IEEE 802.15.4, which is an example of a low-pan link layer. And what we can see is that TCP IP headers are very small compared to the Ethernet and Wi-Fi MTUs, but they're significant compared to the IEEE 802.15.4 MTU. And this is going to result in large header overhead. Okay, normally we size TCP segments to be as large as the link supports, but no larger. This is standard. This is what's used in Ethernet and Wi-Fi. But in the case of IEEE 802.15.4, it's only 104 bytes, right? Our MTU is small, and our TCP IP headers can actually take up more than half of that if you include the cost of TCP options, even if you use a standard IP header compression that's part of 6LoWPAN. And what that means is that if you're transmitting data in a TCP connection, more than half of the data you're sending out are just these headers, and your goodput is severely affected by that. So in order to overcome this, we break this conventional wisdom and instead allow TCP/LP to have TCP segments that span multiple link layer frames. Okay, what that means is that we're relying on the 6LoWPAN adaptation layer to handle fragmentation and reassembly for us, which adds some overhead. But it means that the overhead of our headers is now amortized over multiple frames, allowing us to get some good goodput. Now, there is a trade-off here. If we use too much fragmentation, if we set our MTU, if we set our TCP segments to be way too large, what's going to end up happening is that we rely on too much fragmentation, and that's bad because now if one fragment gets lost, we lose the entire packet. So what we want to do is we want to choose our TCP segments to be as large as possible to effectively amortize the overhead without incurring more fragmentation beyond that. Okay, and this graph shows our experiment where we measured the maximum segment size and the goodput that results, and we found that the gains essentially level off around 3 to 5 frames. So that's what we use for our future experiments, and it shows that there's a good trade-off to be made here, where we can get goodput despite the header sizes. Now, one thing that we didn't do but could potentially help in a way that's orthogonal to this is to get good TCP header compression, right? Because 6LoWPAN currently standardizes UDP header compression with 6LoWPAN, but not TCP header compression, and that's another opportunity to reduce these overheads further. Okay, now I'll talk about how the link layer scheduling to support a low duty cycle interacts poorly with TCP. So recall that these devices often don't have enough energy to keep their radios on and listening all the time. So we define the duty cycle as the proportion of time that the radio is listening or transmitting. Basically, the percent of time where the radio is not in a low power sleep state. Okay, and in order to get good energy consumption, we want the duty cycle to be as close to 0 as possible. Now, there are several ways in order to support this in the substantive literature. OpenThread uses a particular duty cycling mechanism that's called a receiver-initiated duty cycle protocol, which I'll now explain. So in OpenThread, you have two kinds of nodes. You have battery-powered nodes, where we want to minimize the duty cycle, and wall-powered nodes that are plugged into a wall outlet and have enough power to keep their radios always on. Okay. Now, sending a frame from B to W is easy because W's radio is always on. So we can just send the frame whenever we like. More challenging is the reverse, getting a frame from W to B. Okay, so what has to happen is that W has to wait until B's radio is listening. And how does it know when B's radio is listening? Well, this is where the protocol comes in. What B does is that whenever it turns on its radio to listen for a frame, it'll send a data request packet to W, informing it that it's now listening. So W has to wait until it gets its data request packet, and once it does, then it can go ahead and send the frame to B, and B will listen and receive the frame. Okay, so what's the key point here? The key point I want to emphasize is that B's idle duty cycle is directly related to how frequently it sends data request frames. B can choose to send data request frames very rarely, which allow it to get very good energy consumption, but doing so would cause more of a delay in getting frames to it, since W has to wait for the data request frame in order to send it one of the data frames. Okay, so now let me talk about what this means for TCP operation. And I'll do this by comparing HTTP over TCP to CoAP. Okay, and CoAP is a REST-based protocol running on top of UDP. And in our setup, we had B send W a data request frame every 1 second. Basically, it wakes up to listen for packets every 1 second, and that allows it to get a really low duty cycle. Now, the key difference between HTTP and CoAP here is that HTTP requires 2 round trips, whereas CoAP only requires 1 round trip. Okay, so for the first round trip, right? You start at a random phase within the 1,000 millisecond sleep interval. So you'd expect on average a 500 millisecond delay, and CoAP is consistent with that. For HTTP, what happens is that for the first round trip, we see 500 milliseconds. But the second round trip starts right at the beginning of the next sleep interval. So the second round trip consistently sees the worst case latency when transmitting the packet from W to B. Okay, and as a result, HTTP performs more than twice as poorly as CoAP on this workload. Now, I want to point out that there have been some recent extensions to TCP, for example, TCP Fast Open, which you can use to eliminate the second round trip and get performance parity between CoAP and HTTP. But this problem also happens for bulk transfers, where the ACK clock nature of TCP causes it to consistently experience the worst case latency, even for bulk transfers. So this is an important problem to solve regardless of that. And our approach to solving it is to use an adaptive duty cycle. The idea is that we can use the TCP and HTTP protocol state in order to vary how often we send data request frames. The idea being when we expect a packet, we want to send data request frames more frequently. So for example, if I'm an HTTP server in one of these battery-powered devices, and I just accepted a TCP connection, I can be pretty sure that I'm going to soon receive an HTTP request on that connection. So I may choose to send data request frames more frequently at that point in time. And doing this nearly entirely eliminates the gap between CoAP and HTTP in terms of performance. So if we zoom out and look at the overall network, this adaptive duty cycle technique works well for the last hop, going from a wall-powered node to a battery-powered node. But the overall network still has to operate over multiple wireless hops to even get to that last hop. And what we observed is that TCP performs poorly over this chain of wall-powered nodes due to hidden terminals. So let me step back and go over hidden terminals to provide some background on that for those who aren't familiar with it. We can understand the wireless range of a node as looking something like this. The unit disk model is a simplification where we consider this to be, in some sense, a perfect circle. In practice, of course, it can be more complex depending on the exact environment your deployment is in. But unit disk model is going to be enough for us to capture the phenomena of interest here. So we'll go with that. So imagine you have 4 segments in a line. I mean, four nodes in a line with their transmission ranges shown here, and we want to transmit data from A to D. Now, the nature of TCP is that we have multiple segments in flight at the same time for a single connection, and that's why we have segment 1 being sent from C to D and segment 2 being sent from A to B. But unfortunately, this is bad because the wireless ranges are going to overlap at B, so the 2 packets are going to interfere there. Okay, now in the context of Wi-Fi, we typically overcome this using a protocol based on RTS and CTS frames that allow us to mitigate the hidden terminal problem in most cases. But in the context of low pans, the small MTU means that RTS, CTS typically has too high of an overhead. As a result, most uses of it don't use RTS and CTS packets. So as a result, we're only relying on CSMA, right? So at A, CSMA can't detect C's transmission because it's all the way, because A is out of range of C, and CSMA at C can't detect A's transmission because C is out of range of A. But both of the packets end up interfering at B, and the packet gets lost. This also happens because of data packets and ACKs going in opposite directions. So for example, here, what we'll ultimately see is that you get the same problem with B and D both sending at the same time to C because each of their CSMAs can't hear the other. So to mitigate this, our approach is to add a new random backoff delay between link layer retries. Okay, so the idea is if you transmit a frame and it fails, which you know because you don't get a link layer acknowledgement for it, then you wait a random amount and retry the transmission. And this is different from CSMA in 2 respects. The first respect is that in CSMA, you do this randomized delay with exponential backoff if the channel appears busy. In this case, even if the channel appears clear, if our transmission fails, we still do the backoff. So it's different in regards of what triggers the transmission. And second, it's a much longer delay, right? Because in CSMA, you can rely on hearing a concurrent transmission. You can transmit immediately if the channel appears clear. In this new delay that we're adding, this link retry delay, what we're seeing is that we want to have a delay that's chosen between 0 and 10 times the time to transmit a frame. The idea being, even if there are two concurrent transmissions that can't hear each other, with high probability they won't overlap in time. Okay, so the way this would work is that each of these two nodes would send its data once in order to go, and they would collide. But then when they retry, they'll transmit a second time at hopefully different intervals, and they won't overlap in time, and the transmission will succeed. Okay, so we did a measurement study to understand what kind of link delays would be appropriate and what would work. What we observe is that there's a huge reduction in packet loss, even from a small delay. And as if you increase the delay too much, it starts to eat away at your goodbit, because now you're waiting a lot when transmitting your packets. So we found that there's a sweet spot here at around 40 milliseconds, which is about 10 times the time to transmit a single frame in IEEE 2.15.4. So that's what we used in our study. And this reduced the packet loss rate from 6% to 1%, which we consider a significant improvement. So finally, I'm going to summarize our evaluation and conclusions. So first, I previewed this result at the beginning. We're able to achieve significantly higher goodbit than prior attempts at using TCP, and we're very close to a reasonable upper bound that we computed based on measurements of how fast the radio can send out packets and the overhead loss to headers and ACKs. We also did a measurement study to study the energy efficiency. So we used TCP and CoAP for a send task and measured the radio duty cycle over a 24-hour period. And you can see the radio duty cycle here. The key point is that TCP is not significantly worse than CoAP. In fact, they perform comparably for the duration of the experiment at about a 2% duty cycle. And we consider this a success because TCP is able to perform essentially on par as a protocol over UDP developed specifically for low bands. So now that TCP is a viable option, what does this mean? Well, first, we should reconsider the use of lightweight protocols that emulate part of TCP's functionality. In the sense that, if you have a protocol that's specialized and performs just as well as a general protocol that's more interoperable and used more broadly, we should perhaps prefer the one that's used more broadly and is more interoperable. Second, we think that TCP may influence the design of low-pan network systems in the sense that, for a long time, it's been the case that many smart home devices that you buy on the market require a specialized gateway to get internet connectivity. And TCP gives us the opportunity to allow these devices to connect end-to-end to any services externally that they may depend on. And finally, I just want to mention that UDP-based protocols, I think, will still be used in low bands, but just in the same sense that they're used broadly in the internet for applications where specialized protocols substantially outperform TCP. In cases where TCP performs on par with the specialized protocols, using TCP is now a viable option. So just to talk a little more about the middle point, about how TCP may influence the design of low-pan network systems, when I say gateway architecture, I mean a setup like this, where you have your devices, these smart home devices you bought on the market, and in order to allow them to communicate with some application server in a data center somewhere, you have to install some specific gateway in your home that is some protocol translation and application logic in order to bring connectivity to those devices. What this means is often the case, and some of you may have experienced this, is that if you go buy smart devices from a new vendor, now all of a sudden you need another gateway for those new devices, or even maybe the newer versions of devices from the same vendor. Like for example, for a long time, it was the case that if you have bulbs from say LifeX and bulbs from Philips, you would need separate gateways for both of those devices. The introduction of IP in this space didn't really change this in the sense that now your application protocol on the left is now implemented over IP, but you still need the application layer gateway. And the missing piece, I think, that would allow an end-to-end connection here would be to have a transfer protocol that's supported on both sides, namely TCP. And once you do this, your application layer gateways become regular border routers, and you could potentially consolidate these together into a single border router. So in conclusion, we implemented TCP/LP, a full-scale TCP stack for low-pan devices. We explained why the expected reasons for poor TCP performance don't apply. We show how to address the actual reasons for poor TCP performance, and we show that once the issues are resolved, TCP can perform comparably to low-band specialized protocols. That's all I have prepared, and I'm happy to take any questions now.
Okay, thank you, Sam, for that excellent talk. I see we have a couple of people in the online queue and a couple of people at the microphone. Should we do I guess that we'll do the microphone first. So I can't see who that is, but if you can go ahead and say your name and your question.
Yeah. So, hi, I'm Matthias. I'm one of the co-founders of Wired. Great work. Thanks a lot. One remark and two questions. Question first. So you argued that supporting TCP is important because it's popular. Now Quick becomes popular. Did you work on any comparison from a system point of view?
Sorry, I didn't quite hear what you said becomes popular.
You said that TCP is popular, but Quick also becomes popular in the internet. Quick, you know? Quick. Quick.
Quick, yes.
Yeah. So
Yeah.
did you any comparison?
So we didn't do a comparison against Quick, but I'd like to comment on that because that's a good point that the other transports are becoming popular. Many of the issues that we addressed aren't specific to TCP. They apply broadly to TCP and other protocols needed for bulk transfer. Like, for example, the main issues, getting it to work with hidden terminals, getting it to play well with link layer scheduling, and so on, apply broadly to any protocol that's transmitting a lot of data and wants a significant amount of bandwidth. Therefore, I think that many of our conclusions would actually apply equally well to Quick as they do to TCP.
Okay. And another question, I mean, in your paper, you note that you also have an implementation for GNRC, the default network stack in Wired. Do you also plan to submit a PR to upstream the implementation?
At some point, we did have plans for that, but what happened is that Riot OS already adopted a different TCP stack, and it seemed a bit redundant to contribute a second one. Recently, what we have done is we've instead contributed our code to OpenThread, which now uses it as its default TCP stack. Okay.
But still, I highly encourage you to submit a PR. And final remark, you said that a fragment needs to be, a packet is lost when the fragment is lost. I mean, this depends a little bit on the fragmentation scheme, right? If you consider, for example, selective fragment recovery, it doesn't matter too much whether a fragment is lost or not for the whole packet.
Yeah, so my understanding about the way 6LoWPAN worked, or at least the way it was implemented in the operating systems we looked at, was indeed that if a fragment is lost, you lose the whole packet. But I do agree that there are protocols you can use to recover a lost fragment without losing the entire packet. And those could also help with the problem, allowing you to make the packet bigger and amortize TCP IP headers even better.
All right, hello. Tommy Pauly from Apple. Thank you for doing this talk. Very interesting. I'm super happy to see the use of TCP here. I just had a couple questions from the presentation. Way earlier, and you don't have to go back, when you're talking about the memory saving aspects and the ability to have the flat buffer, you had the diagram there of, essentially here's kind of what's in flight, and then there's the out of order bits. And there are gaps in there as well. When you're doing this, are you able to essentially guarantee 100% of the time that you'll never need to allocate memory, or is it like just most of the time, and then there would be a failover case where you do need to have dynamic allocation?
That's a great question. We ensure that you never have to dynamically allocate memory.
Cool.
And the way we do it is that you store the data there. You have a bitmap to keep track of which bits contain the out-of-order data. But the bitmap can also be sized statically because it depends only on the array size, which is also static.
Got it. Okay, cool. And then the other question is more about kind of what you're ending with, talking about how you can use this to get to internet hosts end to end. And I believe in your tests, you were testing against end-to-end internet connections. For that, do you need to modify anything on the TCP implementation on the internet servers? Because we were mentioning things like timing, the retransmit timing schedules that you want to add randomness so you're not colliding. Is this something that needs tuning on the internet hosts to make sure that they are friendly to the low-pan devices, or can you use completely unmodified internet hosts to talk to?
Yeah, that's an excellent question. And the short answer is that the hosts on the Linux side were completely unmodified.
Great.
Cool. I mean, that's to say a little bit more about that. The timing that we adjusted for like the randomized delay was not at the TCP level, it was at the link layer. So as a result, the other side actually doesn't see any of that.
Got it.
This is also one of the advantages to us using a full-scale TCP stack like the one from FreeBSD, because it's been battle tested in the real world and it's interoperable with all of the major TCP stacks that are out there. And I just want to say that interoperability is actually a problem in the embedded space. Many of the embedded TCP stacks you find have interoperability problems in pretty subtle ways with the real TCP stacks that are used. And that's something we managed to sidestep by using a battle-tested TCP implementation as the basis of our study.
Cool. Thank you.
So hello, this is Thomas, also from the Riot community. Thanks again for this work. Thanks for using Riot. There's another encouragement using GNRC because you have a generic packet buffer here, which you could reuse that even reduces your memory overhead even further. Just a remark. One question about your multi-hop experiments. You showed us nicely how by jittering the TCP forwarding, how you could avoid the hidden terminal problem. Was that in a clean environment without cross traffic, with only a single TCP connection?
Yeah, so the hidden terminal problem affects even a single TCP connection in isolation. And we verified that our randomized backoff fixes the problem in that case.
Yeah, but only in this case. I mean, the normal case is that you have background traffic, right? So,
yeah. So, I mean, if we have background traffic, this is also why we use randomized delays instead of fixed delays. Because if we had a randomized backoff, it doesn't matter the interference is coming from the same stream or a different stream, right? In both cases, you'll back up a random amount and hopefully transmit again without colliding. This is also why we did it because I mean, there are several protocols you could use that look at TCP state in some way. And having it just be a randomized delay the link layer gives us some confidence that it would work across TCP streams and regardless of the source of traffic, whether it's TCP, different TCP streams, or even something else.
In this context, did you also consider experimenting with more flexible link layer, MAC layers than just CSMA-CA, for instance, the DSME MAC layer, which is also supported by Riot?
No, we didn't experiment with that. We looked at CSMA because that was the most common one supported across all the operating systems and networking protocols that we tried across TinyOS, Riot, and OpenThread. So it seemed most natural to focus on that.
Okay, thank you.
Thank you.
All right, thank you. I think we have a remote question. Dave Moran.
Am I unmuted finally? So this is following up on the multi-hop case. So in these environments, the forwarding devices are in fact also very low power, low resource devices. Did you see or could you speculate on what you might see as to whether TCP traffic would have more stress on the buffers of the forwarding multi-hop wireless nodes?
So that's a great question. First, first, I just want to clarify that the buffers used at the intermediate routers, these aren't TCP layer buffers. These are just like the general packet buffers used for forwarding because, in an end-to-end TCP connection, there's no TCP state.
Sure. But it may put a different load, aggregate load on those buffers than, say, co-op traffic or something that's more, simple request response related.
Yeah, so I mean, of course, it's the case that when you're transmitting at higher bandwidth, you're going to place some more stress on the buffers of the intermediate routers. And there are a couple things that we actually did in our study in order to help mitigate that. The first one is that we added some active queue management functionality to those intermediate routers, where you mark packets as congested using explicit congestion notification and so on, in order to prevent TCP from filling up the entire buffer and keeping your queues short. The primary reason we did this was to improve fairness of different TCP flows that are competing for buffer space in these intermediate routers, and also to reduce the latency of traffic. But it also has a side effect of limiting the amount of buffer space that's being used by a single TCP flow to address some of the concerns that you brought up.
Thanks. I was looking for the AQM angle on that.
All right. Thank you. So I have a question. Does the I very much like the idea of letting the header span multiple link layer frames. Does this put any constraints on the link layer, or does the 6LoWPAN layer sort of handle all of that?
That's a great question. So some of these can potentially be handled at the 6LoWPAN layer, but others do indeed have to do with the link layer directly. Like for example, the randomized delay that we added to avoid hidden terminals is something that would operate at the link layer, right? Because at the 6LoWPAN layer, you don't have, or at least you don't naturally have the same kind of visibility into, when your link layer acts are coming in and so on. Whereas you would need that to determine that a transmission failed and how much to back off on the retransmission and so on. So some of them do indeed affect the link layer.
Yeah, are there requirements that the link layer delivers packets in order to avoid damaging the headers, or is 6LoWPAN handling that?
Sorry, I didn't understand your question.
Is there a requirement that the link layer delivers packets in order, because of the way you've sent the headers split across multiple link layer frames, or is that all the reordering handled by 6LoWPAN?
Oh yeah, so the reordering and reassembly is handled by 6LoWPAN, and there's no strict requirement that you have to transmit the frames of a packet directly one after the other consecutively. In fact, one of the things that I skipped because of the time limit was another set of techniques we have at the level of managing how to deal with concurrent frames, basically how to schedule frames when some of them are going to other wall-powered devices, some to battery-powered devices. And in effect, what we do is if you receive a data request stream from a battery-powered device, then you prioritize sending frames to that in order to reduce its duty cycle and let it go to sleep as fast as possible. And that's one case where we specifically might interrupt another transmission and not send its frames concurrently. I mean, not send its frames consecutively.
Oh, okay, yeah, that makes sense. Thank you. Gabrielle, you have a question?
Me? Hear me well? Okay. Yeah, thank you very much for this work. This is great stuff. I did have a comment on the comparison with CoAP. I think the justification for CoAP was not entirely based on we can't use TCP type thing. It was more based on we can't use HTTP, because the justification for it was for folks who wanted to use a RESTful interface for the application layer. Not every application layer in IoT wishes to do that, but there's certainly a lot of incentive to use RESTful. So when the RESTful folks started to become interested in IoT, the only alternative was HTTP 1.1, which I completely agree is terrible. It's a non-starter. It's textual-based protocol. You cannot compress it. It's very verbose, etc. It's terrible. We subsequently had HTTP 2, which became a binary protocol, and we actually had a paper 3 years ago in ANRW about how to use that over something like 6LoWPAN, for example. Some just initial scratching the surface, but now we have HTTP 3 and QUIC, and it's all binary. So I understand you guys haven't had a chance to go after the excellent work you've done to look at those layers, but I would highly encourage you to do that, because that would address a significant portion of the application layer incentives for IoT as well.
Yeah, so thanks for clarifying that. I do acknowledge that CoAP has evolved quite a bit in a few years. Some of those evolutions happened after we published this work, but I do want to clarify my position on CoAP a little bit based on what you said. It's that indeed, I think that CoAP is useful and it has its uses and it's very flexible. It's been evolving a lot over the years, and that's great. I have noticed that CoAP has been evolving in some sense more and more towards the same kind of abstraction that TCP provides, right? In some sense, the ability, like for example, with some of the recent work on streaming block transfers and so on. All I'm saying here is that I think that an application that's built on CoAP in these kinds of networks with all the latest features, like for example, the ability to have multiple blocks in flight concurrently and so on, would also be wise to potentially consider using TCP directly itself, given that TCP is also a viable option in these networks. But thanks for that comment.
All right, thank you. One more question. Benjamin Zeltzelnik, was it?
Hi, thank you so much for the presentation. I really appreciate it. I was just wondering, you talked mainly about the applications of this in LANs. Do you see any application for longer range networks like mobile ad hoc networks or anything of that sort?
That's a great question. So all of our experimentation was done using IEEE 15.4, which is a personal area network protocol. And that was motivated by the recent interest in adopting some of that technology to work in the smart home and IoT space. Some of these lessons might carry over to the mobile and ad hoc network space like LP WANs and so on. I'm not sure I'll be able to tell you any specifics given that I don't have much experience with those networks. But I mean, my first gut would be there's probably a way to make TCP work well, given that it's been adapted to work in so many different kinds of networks in all kinds of different environments. But other than that, I'm not sure if which of the specific techniques would directly carry over there.
Thank you so much.
All right, thank you very much for excellent talk. And thank you again to both of the speakers. I think there were two really great talks there. Both Sam and Tasha will be around all week. I'm sure they'll be very happy to talk with people more about their work. So please do find them, have a chat about their work, make them welcome to the IETF and to the IRTF. Congratulations both to Sam and Tasha for the award of the ANRP this time. As I said earlier, look out for more ANRP award talks at the IETF114 in London in November. The nominations for the 2023 ANRP awards will be opening in September. So if you know any good work, please think about nominating that work. And look out for the Applied Networking Research Workshop, which is taking place co-locating with the IETF in Philadelphia tomorrow. Thank you again, everybody. Hopefully, I will see some or all of you in London or at the NRW tomorrow or later this week. Thanks, everyone.